I want to talk to you about what's happening underneath our feet and the reasons that we are witnessing those increases are directly linked to forces even beyond our planet that are influencing the core of our planet. We're a community. We've got the same concerns. We're hearing the same information, and we've got the same questions about what it is that's happening in our world and our lives. How important this magnetic field really is. It influences all life. Every form of life. So one of the questions is, where does this field come from? So scientists estimate that we may have as many as 100 million species, that we're losing them at a rate of approximately 10% per year. 10%. And probably stopped is what the scientific data is showing. The outer core is still chugging away. It's still the currents are still moving in the same direction. The cosmic ray coming in, hits the atmosphere, bursts into a bajillion pieces. How can you trace those back to the source of their origin? Because now their trajectory has changed. Cosmic rays can trigger a core shift, and here's how it can happen. I think most people who are watching this program know that there is a magnetic field that surrounds our planet and looks very similar to what you're seeing on the screen right now. There is a North Pole, there's a South Pole. There are magnetic field lines that surround our planet. You're seeing a cross-section of it on the screen. And the result of that magnetic field is essentially like, you can think of it like a bar magnet in the center of our planet. North end of that magnet is pointing to the North Pole. The south is pointing to the South Pole, like you're seeing on the screen right now. A lot of people, however, do not realize how important this magnetic field really is. It influences all life, every form of life, from microbes and bacteria to every blade of grass, every tree, every plant, every mammal, every reptile, every insect, and every human. We are all deeply influenced by these fields on a biological level, and that is a conversation beyond the scope of what I can do well in this program. But on a physical level, we could not survive if this field did not exist. And the illustration that you're seeing, what you're seeing on the screen, tells us precisely why this is. So what you're seeing, you see the planet Earth there, the little blue ball in the center, and you see these funny shaped lines that surround the planet. These are the magnetic field, and on the right-hand side, they are elongated, extending into space, but on the left-hand side, they are compressed and deformed. And this picture shows you precisely why that is. On the far left, what you're seeing is our sun. It is the energy from the sun, the cosmic rays, the solar wind incoming from the sun that is pushing against the magnetic field on the side that faces the sun. And our field is the shield that protects us from those damaging rays. If we had no magnetic field, life could not exist. Electronics could not exist without that field. The intense radiation would burn us. It would burn our planet. Our electronics couldn't function the way that they do today. So the field is very, very key to our very existence. So the field is important to us. And I want you to see this image. This is actually a NASA image. Our planet there is that little ball in the center. The sun is still to the left, and you can still see that the lines of the magnetic field are still deformed to the left. But you can see in motion how the solar wind actually moves and changes the shape of these fields as they are protecting us from that solar wind. So one of the questions is, where does this field come from? Well, to understand the significance of what the inner core is doing, we've got to understand where this field begins in the first place. So let's do a little cross section of our planet. I'm amazed how many people that I speak with that believe the Earth is just a solid ball, or maybe there's some molten magma underneath. But it's actually very well organized. And what you're seeing on this cross section, if we could pull the Earth apart and look at this, the outer layer obviously is called the crust. This is the layer that we live on. It's the mountains and the oceans and the land. It's only about 36, it averages about 36 miles in depth. Below that, we have what is called the mantle. And the mantle averages about 1,800 miles in depth. It's the orange that you're seeing on the screen. And it is hot. It is a plastic kind of a molten material. It's not 100% liquid, but it is so hot and it is under so much pressure that the minerals are said to be acting with a plastic consistency. Inside of that mantle, you see the yellow, and then at the very center, you see the white. The yellow and the white together are called the core of our planet. So even though there are two aspects to the core, they are called the core. The yellow is called the outer core, and the white is the inner core. The white is where all the controversy is right now. So let's take a look at this a little bit different cross section. Right there in the center of the screen, what you're seeing is an artist's conception of the inner core, but now we know that there's even more to the inner core. There's actually an inner core, another inner core that scientists have found through the action of seismic waves from earthquakes. As scientists measure the seismic waves of the earthquakes and they go down into the center of the earth and then they're reflected back, the density of the material changes the speed of those waves, and scientists can register those, and with that, they can map the inside of the planet. So now it appears that there is actually an inner core within what we have always thought of as the inner core in the past. So these two, the inner core and the inner core, are believed to be solid. And the reason that they are solid is because the pressure is so great at the center of the planet, and the heat is so intense, the pressure is so great it cannot become a liquid. So this inner core, where you see the white, and now we know the spot, the darker spot within that, they are made primarily of iron and nickel, is what this inner core is composed of, and it is a crystalline substance. So it's a crystalline iron nickel. The outer core is a liquid, and it is also an iron nickel outer core. And this is important because the magnetic field of our planet is the result of what's happening between these two, between the inner core and the outer core. So the inner core of our planet does two things. It is a source of tremendous heat. As the inner core heats up, by convection, that heat is carried into the outer core, and then the outer core, because it's a liquid, actually has convection currents. So these currents are moving in the liquid around the solid inner core that is primarily iron and nickel. This is what creates the magnetic field. It's kind of like, maybe you did this experiment when you were a kid in school. If you took an iron nail or an iron bar and you wrap copper wire around that iron nail or the iron bar, and then you attach one end of that copper to one end of a battery and the other end to the other end of a battery, now you've got a current passing through the copper winding around the stationary iron in the center. So what's happening is that electricity is moving. These are electrons moving through the wire around that iron, and it is that motion that creates the magnetic field. Well, that principle is in play here. It's the motion of the iron nickel liquid around the relatively solid or the crystalline inner core of iron and iron nickel that's creating the magnetic field. It extends through our planet and beyond our planet into space. And you saw the image. This is what protects us from the incoming cosmic radiation and solar wind and things like that. So the inner core, this is where the action is. This is what's in the news right now. It does a couple of things. It creates the heat that by convection from the inner core is carried into the outer core, but it is floating in that outer core. And as it floats, it's not stationary, it oscillates. Sometimes it rotates in one direction, sometimes it rotates in another direction. Sometimes it's not even in the center, it actually will bounce on occasion up to the boundary of that outer core. So this is the way it works. The heat from that solid inner core creates the convection currents in the molten iron and nickel in the outer core. So here you can see an image. There's the inner core, and those little curly Q arrows are the convection currents in the outer core. And those convection currents create the magnetic field that extends beyond the Earth. What kind of temperatures are we talking about? Well, the inner core temperatures are estimated to be around 9,392 degrees Fahrenheit. That's almost, we're approaching temperatures of the sun at that point. And the outer core is 9,032. It's a little bit cooler. So it's that differential that allows the heat and the convection. So again, it's the motion of the outer core around that inner core that's creating the magnetic fields in the North and the South Pole that we see as, all the illustrations that we're seeing. So I wanted to just spend a little bit of time on that so it's clear on where this magnetic field is coming from, because sometimes the field shifts. Every once in a while, the poles will shift 180 degrees or they will reverse. In other words, what will happen is the North becomes south. And I'm not saying that the Earth turns physically, but the energy of the magnetic field flips. So what we think of as the North Pole in the Arctic becomes the South Pole. And what we think of as the South Pole in Antarctica becomes the North Pole. What you're seeing on your screen right now, I want to call your attention to this. It's really interesting because normal polarity, this is going to be a very, very different way of thinking. Normal polarity on the left is where the North is in Antarctica and the South is in the Arctic. Every once in a while, as I said, there's a flip and the reverse polarity where the North becomes our North Pole today that we think of, and the South becomes the South Pole. So we are living the results of the last magnetic flip, and that flip happened to be reverse polarity. We are living a time of reverse polarity. How do we know that these flips have happened? Well, we can measure them geologically, and it's fascinating to me, and just share briefly how we know this. There is molten material that has that is magnetically inclined in the Earth. When that molten material becomes hard, it will freeze those magnetic particles in the alignment of where North and South Pole is in that moment in time. So we take core samples and we can go down and we can see the reverse of the polarity back and forth. We know that this has happened. A complete pole reversal has happened at least 20 times. We can measure 20 reversals in the last 5 million years. And you're seeing those on the screen right now. The black is the reversal and the white is the normal. So where we are right now is right at a boundary that happened at about 780,000 years ago, 780,000 years BP, before present. And I'm going to draw that boundary just above so you can see the number, 0.78. It's the fraction of the time scale. And it has a name. It's called the Bruns-Matuyama boundary is where this is. Happened 780,000 years ago, and we are still living the orientation that the poles flipped into 780,000 years ago. Now, one of the mysteries about these reversals is they appear to be random. The scientists go back further and further in time, and they can measure these. There is no regular periodicity. There's no cyclic rhythm that determines when this is going to happen for the pole reversals themselves. All right. So I want to be really clear about this. And I just mentioned that before the poles can reverse, and I want to be clear on this because so many people ask me and some people are frightened and just don't know what this means. So I want to set your mind at ease from this respect, in this respect, at least. Before the poles can reverse, two things have to happen. The first thing is the strength of the magnetic field must drop to a low level. It's got to reach a minimum threshold. And then once it reached that, it's like free fall. It just falls, right down to zero. So the strength of the magnetic field must fall to reach a minimum threshold. So what is that threshold? Well, right now, in recent history, Earth's magnetic field strength, it's measured in a unit, you engineers will be familiar with this, it's called Gauss units. Right now, the field strength, general magnetic field, there are places on Earth where it's higher, places on Earth where it's a little lower, but the overall average strength is between 0.25 and 0.65 Gauss, 0.25 to 65 Gauss units. Before the poles can reverse, Earth has to lose 90% of this. So the average of where we are today, between 2.5 and 0.25 and 0.6, the average strength overall is about 0.5 Gauss. We can say that. All right. The reversal requires a loss of 90% of that 0.5 Gauss. So before the poles can reverse, the strength of the magnetic field in our planet would have to fall to 0.05 Gauss. All right. And you can see we're nowhere near that. The average right now is 0.5. It would have to drop to 0.05. We don't see any reason for that happening right now. That's the first thing. But even if that happens, there's another thing that also must happen. The inner core must reverse the direction, and we just talked about that, and the outer core has to do the same thing. The inner and the outer core have to both reverse direction. So right now, at this time, we're not seeing that happen. The inner core has slowed and probably stopped, is what the scientific data is showing. The outer core is still chugging away. It's still, the currents are still moving in the same direction. We still have a magnetic field. We could have a magnetic field without the inner core moving, because that magnetic field is primarily the result of the convection currents in the molten iron, nickel in the outer core, those convection currents moving. So today, it appears that the inner core has paused, which it does periodically. Some scientists say this is something that may happen as frequently as every 70 years. If you're old enough, you may have seen this before in your lifetime. The outer core at this time has not reversed its direction. All right, so you can see the criteria has not been met for us to have a polar reversal, at least the way that we have known it in the past. Okay, so I'm hoping this sets your mind at ease of all the things to worry about on the planet. I think you can put the possibility of a polar reversal on the back burner. Doesn't mean that it isn't interesting, doesn't mean that nothing is happening. So let me just summarize this. Right now, there's no immediate pole reversal. Now, could that change? There are things that could trigger this reversal, large energy impacts that could shift what's happening in the outer core. What would those be? Well, CME, or coronal mass ejection from the sun. We had a massive solar flare hit the Earth, like happened in 1849, for example. That could be enough to jolt that outer core. Nuclear explosions. I don't think we see from past evidence. One explosion isn't going to do it. If we had multiple nuclear detonations, and if they were done simultaneously, like one after another may not do it. But if they were done simultaneously, or if they were strategically placed, that could upset that the momentum of that outer core. A comet or a meteor impacting the Earth. So you get the idea. Something big, what we call black swan events, something that we don't foresee happening. There's no reason to expect that something from out of the blue certainly could trigger that reversal of that outer core. Now, I'm going to make a distinction here, because just because the Earth is not reversing doesn't mean that what's happening in the core isn't important and doesn't have a big impact in our lives, because there is another phenomenon that is called an excursion. Magnetic fields can have an excursion. Let me make the distinction here. A reversal happens when both the magnetic field in the outer core, as we said, and the inner core are both reversed. That's when you get the polar reversal. An excursion happens only when the liquid outer core is reversed. We're not seeing that yet, but if the inner core comes to a rest or starts to spin the opposite direction, it could influence what's happening in that outer core. And excursions happen much more frequently, possibly as often as every 12,000 years. We know there was a magnetic excursion 12,000 years ago. It's a time called the Younger Dryas. It was a time of abrupt climate change on the planet. It was when the Earth is coming out of the Ice Age, it began to warm, and all of a sudden, there was this tremendous and rapid drop in the temperature. It happened so quickly that woolly mammoths were frozen in the middle of chewing food or in the middle of a footstep. I mean, it was a very, very quick, very dramatic change in temperature that is now believed to be linked to what was happening in the core of our planet at the time. What would cause something like that? Well, two things. Two things can influence what's happening in the core. Let me speak about both of them, one a little bit less than the other. Milankovitch cycles, I will describe them briefly, but I won't go into a lot of detail. The second trigger is cosmic radiation and our relationship to cycles from beyond our Earth, beyond our sun, even incoming from other parts of the galaxy and possibly beyond. So the Milankovitch cycles are about our relationship to the sun. The cosmic radiation is our relationship to incoming radiation from beyond our sun. So let's take a look at Milankovitch cycles. Earth does not do just one clean, neat orbit around the sun. Remember when I was a kid in school, my textbooks used to show this perfectly circular orbit that Earth was doing around the sun, and Earth was always oriented the same direction no matter where it was. Well, nothing could be further from the truth. Earth does a dance. That dance has 3 phases. One of those is called precession of the equinoxes. If you studied the phenomenon of the 2012 phenomenon, the Mayan calendar, that was all about precession of the equinoxes. These are approximately 25,000 year cycles to do one complete precession. The other is called eccentricity. This is what I was just saying. Earth's orbit is not a circle. It is an ellipse. It's oblong. So you can see there are times if Earth is at the ends of the ellipse on the left and the right, it's going to be further from the sun. The sun's going to have less influence on the planet. If Earth is at the top or the bottom, it's going to be closer and the sun's going to have a greater influence. And we know that. Scientists know this. And then there is what is called the tilt or the obliquity. That's about a 41,000 year cycle. And this is where Earth tilts back and forth on this imaginary axis between 21.5 and 24.5 degrees. So each of these has an influence on the planet. There's sometimes where 2 of these cycles are happening at the same time, and there is a greater impact. Real scientists, not pop scientists, but real scientists know that these Milankovitch cycles are triggers and catalysts for climate change that begin more radiation from the sun coming to the earth, warming the oceans, releasing greater amounts of CO2 into the atmosphere, and then a series of a cascade, a whole series of events that go from that. So these Milankovitch cycles influence what's happening in the core as well. The big one that I want to talk to you about is cosmic radiation. We're only beginning to understand the magnitude of the impact of cosmic radiation. And here's what I mean by the cosmic radiation. I want to put this diagram on here. So you're seeing Earth in the middle, and you're seeing the magnetic fields, the magnetosphere surrounding our planet. But look at what's happening. We're getting a double whammy. We get solar radiation. These are the coronal mass ejections. This is the solar wind we get coming from the sun in one direction, but look at this. In the other direction, we get incoming from our Milky Way galaxy and from beyond what's called cosmic radiation. Cosmic rays are a bit of a mystery. We don't know exactly where they come from, and I'll explain why in just a moment. They are believed to be coming from massive releases of energy other places in the Milky Way and beyond our Milky Way in the universe. A star going, a sun, a star going supernova, for example. So that is where the star burns so much of its energy that it begins to collapse upon itself, and the gravity of collapsing upon itself compresses the energy into a massive release, an explosion. It's called a supernova. That is one of the sources where cosmic radiation is believed to come from, as well as other sources. Again, it is a mystery, and let me show you why it's a mystery. Because when the cosmic rays hit our atmosphere, they fragment, and it becomes very difficult to trace them back to their origin because they are fragmented, because you're seeing many, many particles that are fragmented. And that's what the artist is illustrating in this image here. You can see the cosmic ray coming in, hits the atmosphere, it bursts into a bajillion pieces. How can you trace those back to the source of their origin? Because now their trajectory has changed. Well, cosmic rays can trigger a core shift, and here's how it can happen. The cosmic rays are moving very quickly, and they typically move through most matter, like they're moving through us. If you're in an airplane flying from Europe across the Atlantic to North America, and you're 39,000 feet, you're getting more cosmic rays than the people on the ground. They're passing right through you. But here's the thing. The core of our Earth is so dense that it will not allow those rays to pass as readily. So what happens is the friction from those cosmic rays and the energetic interaction begins to heat the core. The cosmic rays will heat the core of our planet. It heats that super dense inner core. The inner core heats up, and that heat is translated to the outer core, creating those convection currents. That outer core begins to expand, and it actually leaks across the boundary into the mantle. So the iron nickel, that liquid iron nickel in this process actually leaks into, or it finds weak spots. It's projected into those weak spots, and it triggers volcanoes, earthquakes, ocean warming, because it's warming from underneath. Warm water holds less gas than cold water. I think most people know that. Cold water will hold, cold oceans are going to hold a lot more carbon dioxide as the oceans warm, which is what's happening right now. And the ice melts on the poles. All of that is releasing carbon dioxide into the atmosphere, and there is a warming effect that comes from that. Humans are not the cause of that warming effect. So to summarize what I'm saying here, you can see the inner core heats that outer core. The outer core then slips into the mantle, and from what you're seeing on the screen right now, and works its way through preferential pathways, through places where the mantle maybe is thinner, or where the crust is thinner. It does two things. It lubricates plates that are moving on the surface of the Earth, and it also creating more earthquakes, but it also creates more volcanism. And we're seeing both of these things happen right now. We're seeing not necessarily more volcanoes. The ones that are occurring are of a greater magnitude. And you'll see USGS chart in just a moment to show you that. So has this happened before? Absolutely. What we know is that when those cosmic rays hit the nitrogen molecules that are in the air, they're in the atmosphere, the collision between the cosmic rays and the nitrogen creates an element that is called beryllium. And it creates a special kind of beryllium. It's called an isotope, beryllium-10. So what that means is we can look into the Earth for traces of beryllium-10 in the past, and that will tell us that the beryllium becomes what's called a proxy. Can't measure the cosmic rays from 10,000 years ago, but if you see a lot of beryllium in a layer of Earth that's 10,000 years old, you can, by correlation, you can say that beryllium is there because there are more cosmic rays. So it is an indicator of the intensity of the cosmic rays in the past, and it is preserved not only in the Earth, but also in the ice that we see in Greenland and Antarctica, and the ice cores that you've heard me talk about in many of the other programs. So when we are going down into those ice cores, what scientists have done is they've gone back into the ice cores and they say, where in these ice cores do we have high levels of beryllium-10? Lo and behold, 12,000 years ago, a time called the Younger Dryas, we've certainly got it then. There was a scientist who passed recently who I had the honor of knowing and touring with in the 1990s, a brilliant, brilliant man, and he was a dear brother. His name was Paul LaViolette. Some of you may know of Paul. He wrote a very controversial book called Earth Under Fire, where he, as a scientist, as a physicist, went back into the records of Earth's past and looked for something that very few people had ever thought about looking for in the past, and is what he called a galactic superwave. He theorized that every once in a while, maybe every 10 to 12,000 years, something happens in the cosmos, and there's a release of energy that travels as a superwave through the cosmos. It impacts Earth as high levels of cosmic radiation. And as we just said, if that's true, it would create greater levels of beryllium-10, and we should be able to find those in the ice cores. So this is a chart out of one of Paul LaViolette's papers. And all I want to call your attention to is on the left-hand side of the chart is present day. Then you go back 10,000, then you go back 20,000 years. And what you see is right around 12 to 15,000 years ago, you see what he's calling the zodiac arrow. He named it that because the ancient zodiac he believed, gave clues as to the source of this cosmic radiation. The tail of the scorpion on Scorpio, for example, and the archer in Orion, where the arrow was pointed, they all point in the direction of where it appears that these cosmic waves, this cosmic energy is coming from. What he's showing here is right around 12,000 years ago, right around that time frame. Then another one right around 5,000 years ago that coincides with the Mayan calendar, the December 21st date. So, these things don't happen on a dime. They're not immediate. We're talking about ranges of time. Well, what does it mean for today? Well, this is really interesting. This is from the cosmic ray monitoring system that comes from the space weather archives. They measure these things. And what they found was there 4 years in a row, in recent times, between 2015 and 2019, there was a steady increase in cosmic radiation. That steady increase had an effect on Earth. It had an effect on the core of the Earth. Now, I'm saying it in this way because it appears that the radiation is now dropping. This is the good news. Now, look at this. When the new solar cycle began, we're now entering into what's called solar cycle 25. And there's a lot of moving parts here, so I don't want to get lost in the weeds. But one of the things that the sun affords us is when the sun has a stronger magnetic field or multiple magnetic fields. Actually, all the sunspots you see, the sun doesn't have one north and south pole. The sun has many north and south poles, and each one of those is a north and south pole of the magnetic field that we call a sunspot. So when you're looking at sunspots, those are magnetic fields. When the sun has a strong composite magnetic field, it actually helps us. It helps shield the Earth from the incoming cosmic radiation. Well, we have been in between solar cycles, what's called a solar minimum, where the sun is very inactive. There are not many, if any, solar storms at all. So we lose our protection from the sun, and that's what you saw happening between 2015 and 2019. We didn't have much protection there. Now that we are in the beginning now, solar cycle 25, excuse me, has started. the sun is cranking up, the magnetic fields are getting stronger, and they are shielding us from some of that incoming solar radiation, as well as the magnetic field of the earth. Both are working together to shield us, and you're seeing this here. So the good news is that the incoming cosmic rays, the levels have decreased. However, and this is the key, the effect of those previous years is still at work. The effect is still in play. In those previous years, those higher levels of cosmic rays heated up the core heated up the outer mantle expanded and forced that liquid into the mantle, into the weak spots, the preferential spots, creating an increase in earthquakes, increase in seismic activity along the boundaries of the plates, and an increase in volcanoes. And we are still seeing those effects today. They don't stop in the moment that the cosmic radiation stops. Now, in addition to that, scientists, I'm just going to throw another really interesting piece in here. Scientists recognize now through these the seismic waves from earthquakes that they're measuring as they go through the earth and how quickly they move. There are two places on the earth where the waves are not behaving the way that they were expected. They're anomalies. And the technical term for these is large, low shear velocity provinces, or LLSVPs is what they're called. And scientists are now able to map these. I want to show you what this looks like. So what you're looking at is this is the outer core and the mantle that you're seeing, and look at these anomalies now that are above the mantle. These are plumes. They're called mantle plumes. These are places where the magma now is accumulating, and these are the size of continents. I mean, these aren't little anomalies. They're the size of continents. You'll see in a moment. This is where the magma plumes, these anomalies, are accumulating in an unusual way. Now, look at the continents that they are under, and we'll do this slowly so you can see. There's a big plume underneath the Pacific. All right, so you're seeing right here, this is New Zealand. Parts of Australia are impacted by this under the Pacific, and you've probably heard of what's called the Pacific Ring of Fire. These are the plate boundaries from California and Alaska on our side of the Pacific, and Japan that you see, and all of the plates, the way the plate extends from Japan all up through into parts of China and places like that. So look at how big these mantle plumes are underneath the Pacific. Now look at where they are on the other side. They are under Africa, parts of North Africa, and into the Middle East. Now watch where it comes around again, and you'll be able to see this. See Africa and into the Middle East. Why is that important? Well, if you look at the global seismic hazard map, what you're seeing are these are the continents of the earth, and every place where you see red, these are where we can expect high levels of earthquake, seismic activity, as well as volcanoes. And it makes perfect sense because these are the plate boundaries. These are where the plates come together and where the movement is happening. So I'm highlighting one of the hot spots. I mean, recording this map, it's the hottest spot on the planet. And look at where it is. It's in the Middle East. It's Turkey. It's Syria. It extends over into India, Pakistan, Nepal. And if those places sound familiar, they should, because we've had huge earthquakes that have taken many lives, caused a lot of destructions over the last few years in exactly this place. We would expect to see the seismic activity in these places if something is happening under the earth. If those plumes are rising and the molten material from the outer core is coming up into the mantle and creating these plumes, and the plumes are already there. So these are preferential sites. This is where the magma, it's already traveled there. So it's going to want to keep going from there as it breaches the surface through the crust. And it will do it along these plate boundaries. Well, look at the plates where right in here. There's the African plate, the Arabian plate, the Indian plate, and the Eurasian plate. This is precisely where we're seeing these earthquakes. Look at our little, watch when our little globe comes around here once again. I put this up here so you can compare these right there. Look at the top of that mantle plume. Look at Northern Africa, India, and all through the Middle East. In between 1900 and 2018, the USGS has measured magnitude 6 earthquakes. Now, there are many magnitude 1 through 5. Magnitude 6, this is where they start getting really serious and above. And I want to show you what is happening. This is from USGS Worldwide Catalog, so I didn't make this up, but you can see the trend. As we go forward in time from 1900 to 2000 and 2020, the number of not overall earthquakes, but the number of earthquakes that are big, the magnitude 6 on the Richter scale and above is increasing. And that is exactly what we see happening. And in recent memory, just recently was the 2 huge earthquakes right along this place in Turkey. One was a 7.5, one was a 7.8. And look at where these happen. There's the Eurasian plate, there's the Arabian plate, there's the African plate, and they have a different name in that part of the world. They call this the Anatolian plate. But you can see it's where these plates are all coming together. The forces underneath those plates, that magma is lubricating and forcing the plates to move. And some of those places we're seeing volcanoes, and other places we're seeing the movement of the plates. Here was another one that happened, we all remember, in 2015, a huge earthquake in Nepal. Now, it was said to be a 7.8, and there you're looking at the epicenter near Kathmandu is the capital, and this is where we saw all the damage on national media. 7.8, that is a huge seismic event. There was another one in Afghanistan, June 22nd of 2022, more recently. I put this one up here because they said 5.9, it is 0.1 off from being accounted for on that map. The map was accounting for magnitude 6 and above. There is a margin of error, and this very possibly could have been a 6-point magnitude. It was big. It caused a lot of damage, and many lives were lost. So I wanted you to see that, and this is only in one part of the world. I mean, there are earthquakes happening in other parts of the world as well, and volcanoes and potential volcanoes. So what did I just say in all this? What is the summary? And I just want to reiterate what we began with. All the concerns that are out there, as a geologist, I see no evidence for an immediate magnetic pole reversal. So you can set your mind at ease about the pole reversal. We are possibly in the early stages of a magnetic field excursion, which happens much more frequently, possibly every 12,000 years. And other videos will talk about this. And its relationship to catastrophic events that have ended civilizations. And the Great Flood that we read about in almost every major tradition, the Great Flood that came from the rapid warming that occurred when one of these excursions was happening. Another one 24,000 years prior to that. So we know that these do happen. Even though the levels of cosmic rays appear to be decreasing, we are still experiencing the impact from the years where they were increasing up through 2019. So that makes us vulnerable for seismic activity and volcanic activity. Now, this is where it gets really controversial, because there is a narrative that humans are causing global warming and that humans are causing climate change. I've done a number of videos on this channel. We'll link to them, and also on places like Missing Links Season 1 with Gaia. What I can say to you with absolute certainty is that humans are not the cause of climate change. Humans are not the cause of global warming. And I can say that with certainty because humans, anatomically modern humans, have only been here for 200,000 years. When we go back into the ice cores, we see the same rhythms and the same cycles for the warming that we're seeing and the cooling that we're seeing now. We see that back over 420,000 years, and by some estimates, even more than that, where there were no humans, no industry, no technology here. We're not causing it. Are we adding to it? We may be possibly adding to it. If we are, it is not in the amount that will account for what we're seeing. Now, scientists are looking, real scientists that are not paid by politicians, that are not paid by corporations, that don't have a political agenda. Real scientists now are looking, number one, at the Milankovitch cycles. You know, I read a scientific paper, and the question was, what role does the sun play in climate change? And the scientist answered in a way that just astonished me. He said, the role of the sun in climate change is so poorly understood that we don't consider it. They're not factoring it in. Now, that is changing, obviously, but we also know that most of the frightening news that we get is based on computer models and predictions. The models are so inaccurate. The algorithms are so off that even when the year passes and you go back and you plug in all of the exact numbers for the CO2 levels and the temperature and you plug it in the model still cannot tell you what just happened in the year that passed because there's something missing in those models. So I'm not beholden to a corporation. I'm not beholden to a publisher. I'm not beholden to any academic institution or tenure for my, my teaching credentials or anything like that. So I have no problem sharing with you. This is what we know right now. It's not about making anybody wrong. We don't want to make anybody wrong. We want to be honest with ourselves about what's happening. There are factors that are not accounted for in the mainstream narrative that are driving not only climate change and the higher levels of CO2, but they're driving greater levels of seismic activity, greater volcanism, and it has to do with our relationship to the inner and the outer core of our planet, the cosmic radiation that is cyclic, that we are experiencing and where we are right now. So where do we go from here? What do we do about this? Well, obviously, we cannot stop the cosmic radiation. It's happened before. I think the first thing we need to do is be honest with ourselves. How can we solve a problem if we're not honest about the problem? I come back to that question all the time. It makes sense to acknowledge and embrace where we are rather than leading people in a way that is disingenuous, I believe, to think that we can stop the cycles that are progressing, to think that we can stop the sea level rises or that we can stop the CO2 levels if we would even want to. Carbon dioxide, how it's been demonized, the fact that we've had much higher levels in the past, this is not the highest it's ever been, and why we don't want to meet the levels that are being proposed, because in the geologic past, when levels have dropped to 250 parts per million or 180 parts per million, as proposed in some of the models out there, it was not good for the Earth. Forests died, temperatures dropped, ice covered much more of the planet. It was not a good time for the Earth. So I talk about that in those videos. Makes sense to adapt to the cycles that we're in. They don't last forever. And the intensity is something, if we don't acknowledge it, people will suffer. So what does that mean? It means that we should expect sea levels to rise, take our vital establishments away from sea levels, harden the power grid. If we have to have hospitals that are on the beach or hospitals that are on fault lines like we have in San Francisco, Hospital Hill is built right on the San Andreas Fault along with some of the city's vital services. There are ways to protect, at least stabilize the buildings against some level of seismic activity. And they're doing this in San Francisco. I want to give them credit. They're doing this. They're retrofitting the buildings so that they've got some give, so that the earth moves. They're not so rigid that they're just going to collapse. If these are big movements, even the retrofits, I think, are going to be hard pressed to mitigate that damage. So there are things that we can do as communities, or things that we can do as individuals. If you are in a seismically vulnerable zone, It makes sense for now, not forever, but for now, to expect the unexpected. It makes sense to expect that you're going to see an increase, an uptick in these things, and to do what you need to do, be a little more self-sufficient. You're probably going to lose power in an earthquake, have a source of backup power. Probably going to lose good drinking water, and that the water mains will break and be cut off. So have water that you and your family can drink and bathe in. There are ways, I've got videos on this channel that tell you how to store that water and ways that that you can do so for long periods of time. I've got videos about backup power, about backup food. We're living a time of extremes. There are geophysical reasons for these extremes that set now apart from any other time in our past. So it's not about fear. It's just the opposite. The time when we're afraid is when we're not prepared. So if we acknowledge and embrace the truth of what the science is telling us about our time in history, and then we just take common sense precautions, or if you feel that maybe you're drawn to live somewhere else, you've been feeling in your heart and you don't know why, maybe your heart is saying, I'm not saying to move out of fear. I think we are all at our best where our soul sings, where our heart soars. That's where we're at our best. And I think that should be the guideline of where we choose to live. And I want you to know that there are conditions that are happening now that were not happening 10, 15, 20, 30, 50 years ago that make us vulnerable in some places, perhaps more so than others. And we need to bear those in mind, just to be honest with ourselves. So I'm going to stop this presentation. I'll close this edition of In Focus here. I hope we have done just that. I hope we've brought a focus to the concerns about what's happening in Earth's core. I hope you have a better understanding of the dynamics of our planet. They're not teaching this stuff to our kids in schools. They used to. We're not doing it anymore. And I hope this helps you to have a better understanding of what you're experiencing in the world. So when you see this incoming in the news, you have a context within which to place this. We're a community. We've got the same concerns. We're hearing the same information. And, we've got the same questions about what it is that's happening in our world, in our lives. What we're finding today, unfortunately, is that the problems of the world are no longer able to be observed from the perspective of pure science. Most of the problems we're dealing with have been politicized. You're seeing that and I'm seeing that, from healthcare to the climate extremes that we're seeing right now, technology, the way it's being implemented in our lives, politics and greed have come into play in all of these. And we all know that, but the drawback is that it hampers our ability to really address the questions in a meaningful way, in a responsible way, or the challenges that we face as a society in a meaningful way. This is a perfect example of precisely that. What Tegan is asking, I created a video on this channel last year, and I identified a study that was done from the Stockholm Resilience Center. The man named Johan Rockström is the one heading this up. Brilliant scientist. I have a lot of respect for this man. He is really pushing the boundaries when it comes to the way we think of our relationship to the world, because he's looking at it from a non-political perspective, a non-financial perspective, and he's looking at it holistically. And you have to do that. You have to, if you're going to be honest with yourself, if we're going to be honest with ourselves about what we're up against, we've got to look at the big picture. We can't zero in on one crisis or another, which is what we are being asked to do. It's what the narrative coming through the mainstream media, the narrative coming from our politicians. And when I talk about politicians, I'm not talking about just America or just Europe. This is global. Globally, politicians are hijacking science. They're cherry-picking data. They are then funneling that cherry-picked data through mainstream, or what's called legacy media. This is the media on the major networks, the major cable channels. And they're doing it in an effort to drive opinion in one direction or another, so that you and I will make choices. And those choices will be reflected in the way we spend our money and the people that we elect to represent us, based upon what we're being told about the world that we live in. So this is, again, this is nothing new. It's been happening for a while. What is new is the technology has advanced so quickly now, and we rely so much on social media as well as the legacy media that we're being led to believe that there are some really big problems out there that are going to end our lives and end our world if we don't do something about it, such as climate change. And the other problems are rarely even mentioned. So what I'd like to do, let me go back. I will highlight the study from Rockstrom. I'm going to bring up a slide to help us to do that. There are 10 parameters that Rockstrom and his team have identified is what they call a safe operating zone for planet Earth, the safety zone. And I want to be really clear why this is important, because what they say is that all 10 of these parameters must be in place for us to have a healthy planet, for us to continue life as we know it, and for life as we know it to continue in the world. And when these parameters begin to break down, these are the warning lights. These are the flashing red warning lights that we're in trouble. And the reason I'm saying this is because of the 10 parameters that I'm going to share with you, we have already crossed the critical boundary for 3 of those parameters, and climate is not one of them. Climate change is a fact. As a geologist, as a degree geologist, I can say that to you. It is a fact. It is rhythmic. It has happened throughout history. If no humans were on the earth, we would still be going through climate change. Humans did not cause it, and that is a scientific fact. And anyone that tells you that humans have caused climate change either does not understand the climate change or is not being honest with you when they say it. Now, humans are contributing, and we have to say that. As a scientist, I have to say that because our fossil fuel-based economy is creating carbon dioxide and other particulate emissions. We're kicking into the atmosphere, and they become a part of the equation. But the carbon dioxide would be in the atmosphere, and we would be going through the climate change if there were no fossil fuel-based industry. And that is just scientific fact. It's not politically correct. Many of you have heard me say I've refused to be linked to a university. I'm not linked to a corporation, and I'm not beholden to any sources of independent funding. So I have nothing to lose by sharing with you what the data says, as I understand it, as it exists today. And when that data changes, I'm happy to change that story. So climate change, it's important. And yes, we need to manage that. And as I said in a recent video, this is not the warmest the Earth has ever been. Earth has been much warmer when life was thriving. It's not the highest levels of CO2. We've had much higher levels of CO2 when the Earth was very green in the past. The problem comes in because the warming and the rising of the sea levels is threatening our way of life and the choices that we made based upon the climate at another point in time. It's inconvenient for us because rising sea levels will ultimately impact or obliterate seaside communities. Without those communities, we've seen this in the past in the geologic record. We can look at the geologic map, we can look at the ice cores. So I've talked so much about climate change. I'm not going to spend a lot of time on it now. I just wanted you to know, if you're new to this and you're seeing this video for the first time, I'm not a climate denier. Climate's important. Climate is definitely changing. And rather than trying to fight against the climate change, we would do well to learn to adapt to the climate change that is part of the natural rhythms of the planet that we live on. So the image that you're seeing on your screen right now is taken from a paper that was published by Rockstrom's group. He is working with as I mentioned, with the Stockholm Resilience Center. This is he and his team that have put together this report and others. These are very well-known studies in the scientific community. They're not being shared in the mainstream because they don't fit the mainstream narrative. But that's why I want you to see this. I also want to be clear that this is based upon peer-reviewed science. This isn't my opinion. This isn't my theory. If you're going to write to me about my opinions and my theories, I support this work and I believe in it and I think it's true and I think it's accurate and I think it's complete. It gives us a much more complete image of what we're actually dealing with. So this paper was published in the very prestigious journal Nature, volume 461. The year that he published initially was 2009. Now he's continued to do work since and is published since that time. So these ideas have been around for a while, and I wanted you to see this. So what are we looking at here? This is a diagram to illustrate from in terms of proportions. First, what the 10 parameters are that must be held in place, and secondly, where we are in those parameters. So when we begin, let's just start with the lower left-hand corner. When you see that big bright red triangle, looks like a triangle there, slice of a pie, a triangular shaped slice of a pie, that is the parameter of biodiversity. So I'm just going to go around and mention these, and then we'll come back and look at each of them individually. So biodiversity is the first parameter. The second is atmospheric aerosol loading. The third is the chemical pollution in the planet. The fourth is climate change. The fifth is the acidification of the oceans. The sixth is stratospheric ozone depletion. The seventh is nitrate cycle. And right next to it is the phosphorus cycle. These are closely related, but the nitrogen cycle is the one that is in red. And the phosphorus cycle, global fresh water use, and the last one, number 10, is a change in land use. So I wanted to just quickly identify what the parameters are. Let's go back and see what they're saying. And obviously the big one here, biodiversity. We not only have exceeded the limits, we are off the chart. Literally, there's no room left on the chart to show how far we have exceeded the limits in the loss of biodiversity on our planet. Now, in biological circles, this is talked about frequently. You don't hear much about it in mainstream. It certainly has not been politicized. It is tremendously overlooked. What's happening with biodiversity? Scientists don't know for sure how many species of life there are on Earth today. One of the reasons is because there are species that are still being discovered. Every year we are discovering new species of life. Many of them are in the oceans, many of them are microscopic or very small. So not all of them all are like elephants and tigers and things like that. They're very small. However, they're very significant because when it comes to what is called the feeding chain, I know you all have heard of this. In the ocean, the microscopic life becomes the foundation for the next size of life to feed upon, for the next size of life to feed upon, for the next. And by the time you get to the familiar things like whales and fish and crustaceans and things like that, you're already several steps up on the ladder of where these things are. The problem is that the loss of biodiversity in the oceans begins typically at those very low levels, and if those low levels are not there, there's nothing for the higher levels to feed upon, and there's a ripple effect. It's a cascade effect of the loss of the biodiversity. So scientists estimate that we may have as many as 100 million species of life on the planet today, and that we're losing them at a rate of approximately 10% per year. 10% per year. And some of those forms of life, they're disappearing before they're ever identified and documented. We may never know, or we might find them in a fossil record, down the road. We never know what they are. So what does that mean? That would be if we have 100 million species, and we're losing them at the rate that is projected right now. We're talking about the loss of around 10,000 species per year. And even if those numbers aren't right on 100%, in terms of magnitude, you get the idea. It's not like we're losing 10 or 20 or 100 species a year. We're talking about thousands of species a year that are necessary to balance the ecosystems and to balance the environment, including the atmosphere in the environment, because those living creatures are interacting with the atmosphere in very significant ways. So we're off the charts on biodiversity. That's the first one. The atmospheric aerosol loading, we can't really talk about that so much because it is not being quantified. It is a problem. We know that it's a problem. We know that it has to be maintained. A certain level of aerosols and a certain quality of aerosol must be in the atmosphere, and there are toxic aerosols that we don't want in the atmosphere. The next one, chemical pollution. We know that is a problem as well. And also, it is not quite quantified in a way that can be put on this chart. We know it's a problem because of toxic waste, toxic dumping from industry and multiple countries that are doing this. And some of those countries have refused to sign the treaties and the pacts that are agreed upon to work down and minimize the chemical pollution that we're seeing. Climate change, right there in the top of your screen. It certainly is a factor, and you can see, but compared to some of the other things, it's not nearly the factor. And it doesn't warrant nearly the concern because it doesn't have nearly the impact that some of these other things have. Now, climate change, as I mentioned, we have been in a warming cycle. And according to the charts from the ice cores, we should be in a warming cycle. I would be concerned if we were not. If we weren't warming right now and we were at that point in the cycle, I would say, what's wrong? Why aren't we warming? The warming that we're seeing is not the warmest compared to what we've seen in the past. And even with the addition of the CO2 from industry, we're still not at the highest levels of CO2 that we've ever seen. Do we want to reel it back? Absolutely. Do we have the technology to do it? We do, and that technology is not being used. I'm going to talk about that in a few minutes. But I also want to reiterate, if you're seeing this conversation for the first time, you didn't see the other videos, CO2 is a vital, necessary part of our ecosystem. There have been times in Earth's geologic history when the CO2 was lacking and the world dies. Plants die because the plants are breathing. That the forests die because they are breathing that CO2. We need a minimum threshold of 180 parts per million of CO2 or we're in trouble. Now, we're around well over that 400 parts per million threshold. And it is higher than what we've seen in the industrialized era, and the industry is contributing to that. We need to stop burning fossil fuels, absolutely. And we've had the technology to do that for 70 years. If the powers that be were really serious about this issue, I personally would think, is my opinion, I would think they would pull those technologies out of the closet and implement them. The problem is economics. It is less economic to implement technologies that do not emit greenhouse gases than to stay with the greenhouse gas emitting technologies. So climate change, I just want to put this into perspective for you because the narrative that is being shared in the mainstream, the anger that it creates, the division in our families, the division in our communities and society, and the politics that are yielded from that misinformation. I want you to have a perspective of where this issue fits, and you're seeing that now. The acidification of the oceans is a problem, and they're showing it a lower problem here, but it is also linked to the nitrogen cycle because it is through fertilizers, chemical fertilizers that are being used to maintain the kinds of crops that are being grown in the way they're being grown that is contributing to this. So the fertilizers, they don't stay in the field with the crop. Obviously rainwater takes those chemical residues, it percolates down into groundwater, or through surface water, it can run off into lakes and streams, oceans, rivers, and it is a problem. We have to maintain that balance. Stratospheric ozone depletion. Ozone, for some people, is a bad word. I remember back in the 1970s, there was what was called the ozone hole over the South Pole that was accumulating from the use of another kind of ozone, the byproduct of industry and commercial applications. You know, back in the 70s, everything you got in a can was driven by ozone. Everything from hairspray to bug spray to, I've been a musician all my life. My guitar polish was in a can that was driven by ozone. You had to shake it up and spray that polish on your guitar. Everything was. We recognized that, we stopped using it, and to a large extent that ozone hole has healed because Earth is a living biodynamic system capable of healing itself. So the stratospheric ozone depletion is the problem. There is ozone that we need to protect us from CO2, and the depletion in certain areas due to industry has been a problem. The next red cone that you're seeing here, or the next red slice of the pie, is the nitrogen cycle. And as I mentioned, this is largely, not exclusively, but largely the result of pesticides and fertilizers, the way that they're made, the way that they're used to support the kinds of crops that we are growing. There are other ways to grow food, and other ways to grow food that don't require all of the chemical support. We'll talk about that in just a few moments, but that's what you're seeing here. It's very closely linked also to the phosphorus cycle, which is a problem. It's less of a problem right now. Global fresh water use. I think you know that fresh water is becoming a commodity, a rare commodity. In some parts of the world, the amount of fresh water that is available to some populations is dwindling very quickly. And the quality of water that is available in Europe and North America, among other places, has been polluted. The groundwater, when they drill down into the aquifers, some of these aquifers have been polluted through industry, and once they're polluted, they're gone forever. It's very, very difficult to clean an entire aquifer from the pollution that you find. Now, let me share with you a little bit why this is. As a geologist, this is fascinating to me. Because when we talk about an aquifer of water in the ground, it's not like you drill down to a pool or a puddle of water. You drill into the earth, into porous places in the earth. So porosity is very key. And what that means is that between the grains of sand, for example, in the sandstones, there is a space in between the grains of sand. Not only is there a space, but between the grains of sand here and grains of sand over here, the space is connected. There is a continuity that allows that water to migrate. So it's not enough just to have a space. You've got to have a space that's connected to another space that's connected to another space. And that's all about the continuity of the flow and the porosity of the material that it's in. What is happening in large cities, and among these large cities out west in the United States, you see big cities in Arizona and California having water problems right now. And when they need more water, they drill into these aquifers. If they pull the water out too fast, this is the key. If they pull that water out too fast because the population is so big and they need more water to, for all the homes and all the golf courses and all the swimming pools that you can see when you fly over places in Arizona and California, for example. And they pull the water out too fast. What happens, they'll get the water, but here's what happens. Those pore spaces, the water, it's called hydrostatic pressure. The pressure of the water is what keeps those particles separate enough so the water can flow, so it can migrate. If you pull the water out too fast, the particles collapse, and there no longer is communication from one space to another. So now the water, it still may be there, but the water cannot be pulled out because it no longer communicates, it no longer flows, it can no longer migrate through that sandstone, for example. So this is one of the keys. It's not enough to have the water, you've got to have the water, and when you pull the water out, the water has to come out at a rate that allows nature to recharge the aquifer, for new water to trickle down into that aquifer through rain and snowmelt before you pull out more water. Now, I live in the rural areas of northern New Mexico. The Sangre de Cristo Mountains are to my east, and I live in a valley with an aquifer. It's a 2,000-foot thick aquifer, potential aquifer. It doesn't mean it has 2,000 feet of water. But what the hydrologists have found is that it takes about 5 years for the water from the time we get a snowstorm up on the tops, the peaks of the Sangre de Cristo Mountains. That water is going to be there for the season. When the spring comes, it's going to begin to melt. And as it seeps down and trickles and percolates down through the rock, it will take about 5 years for that water to show up in my valley. So, and when it does, it's really good, clean water. And this is the case for a lot of aquifers. It may not always take 5 years, different aquifers are recharged at different rates. Depends on how far away the snow and the rain are occurring. But just to give you an idea, so it's not like if you get a good rainy season, you say, okay, the aquifer's filled, because it takes time for that water to percolate down, and when it does, all the impurities are pulled out through the minerals that it flows through. So when it gets down into the ground, it's really clean water. You've got clean water, if you have access to it, you've got clean drinking water. So this is the problem. Fresh water use, there are the drought that is occurring in much of the world because of where Earth is in its climate cycles. Her climate cycles. Earth goes through climate cycles, and we are in a place in the climate cycles right now where drought is happening, certainly through the western states of the United States. I think we're in this 7th year of a drought right now. We can get some good rain. It's not going to fix the drought. The lakes are low. Groundwater is still low. So I just wanted to say those things. It is really important. It's becoming a big issue. It's becoming a political issue. The potential for wars over water is on the horizon unless we find a way to cooperate and work through this together. And that's why this is important. And the last is changes in land use. We all know that land use, this is important because when you go into a city that used to be a rural community, and all of a sudden you start putting in big office buildings and big parking lots, and you pave over those parking lots, when the rainfall or the snow occurs, that water can no longer communicate with the earth because it's asphalt. So all that water is going to run someplace else, and there are huge expanses where the moisture can no longer communicate with the earth. And it is being concentrated in some places and depleted in other places. The land use, the way it is being used for a lot of agricultural land, is being lost to commercial development. And we see that here in the rural areas of, I was born in rural Missouri, northern Missouri. You see the same thing happening. It's common. We're seeing this a lot. Actually, I'll just be very honest about what we're seeing. We, America, and I'm speaking to Americans, and I think it's a bigger problem in America probably than it is in Europe right now, because America is younger than Europe. So in America, a lot of families have had land in their families, farms, or at least, some kind of acreage for a long time. It was prized. It was appreciated. It was an asset to be passed from one generation to the next. Well, over the last generation or two, the attractiveness of having land has lessened. The value of having that land. A lot of young people, unless they were, raised in a rural family and those values were instilled within them, unless those values were instilled in an early age, they may not see the value of having land. And there are always exceptions. I'm not saying it's everyone, but, and I'm saying that this is happening to a greater degree, and I'm seeing it in my own communities here. So what happens, the land that has been in families for generations, sometimes 300 years, 400 years, as the elders die and they leave that land to the younger people, because the younger people have not been privy to the value of the ability to grow your own food and the value to have that land. When they inherit that land, they don't see the value, and they would rather have the money that the land is worth. So they'll sell that land out of the family. And we're seeing this happen a lot. They'll break up the acreage, they'll sell that land. They say, well, I'd rather have the money than have some land in the middle of nowhere that, nobody's using. So what's happening is that land is being sold, and rather than being sold and maintained as agricultural land, it's being sold and developed as commercial property. So we're losing farmland, the bottom line. That was a long way. I wanted you to understand how it's happening, but that was a long way to get to the statement that we're losing agricultural land. And this all speaks to the change in land use. All right? These are the 10 parameters that are called the safe operating space for humanity, safe operating space for planet Earth. What Rockstrom says is it's not about just one of these. Right now, the focus is on climate change. It's not about just one of these. All of these parameters must be honored, must be held in place, and where they've exceeded the boundaries and we're in the danger zone, we have the ability to reel that in. We have the ability to mitigate the damage and begin the repair and the healing if we recognize that it's a problem. And to do that takes leadership. And when I say leadership, I'm not talking about just a president of a country. It's not just about America or Europe or Australia or Canada. It is the leadership in our communities, the leadership in our families that recognizes that we are part of a whole, part of a greater system, and that we must honor this system and the integrity of this system holistically. We're not talking about just one thing. We're talking about honoring all of these. It's like the human body. You know, in the human body, it's important to maintain all of the systems. We got to keep all the systems functioning. So, you know, if you have a problem with the immune system, you don't put all of your energy into the immune system because you have other systems, cardiovascular system, respiratory system, that have to be maintained as well. We're talking about the cardiovascular and the respiratory systems of the planet when we talk about freshwater use and biodiversity and all of those kinds of things. When we begin looking at these parameters, you know, if we are only putting our energy into climate change, I think many of you probably remember a little game called Whack-A-Mole, where you've got this little mole that pops up in a grid in a number of different ways, and you have a hammer. You see these at carnivals all the time. And, you know, you hit the mole here, and yeah, it takes care of the mole there, but then he pops up over here, and you hit him there, and he pops up over there. This chart works precisely the same way. We put all of our energy into climate, and we're trying to fix climate, which isn't broken. What we're trying to do is force the climate into a place where we are comfortable and we can live the way that we choose to live. That's the truth of what's happening. Because Earth's climate is a dynamic system. It's always changing. It's not static. And we've been led to believe, and the mainstream has indoctrinated many of our young people into believing that climate is a static parameter, and when it changes, something is wrong, something is broken. When in truth, much of our climate is driven by Earth's location in space that changes over time. The tilt, the angle, and the wobble, specifically what's called the obliquity. As Earth travels around the sun, it's not a circular orbit, it's an elliptical orbit. Sometimes we're closer to the sun on the ellipse, and if you're on the end of the ellipse, you're further away. We know this, and every 5,000 years we go through these climate changes. It has changed populations. It has led to the migrations of some of the great civilizations on our planet. So all this is known by the real scientists, the pop scientists, and the ones that are featured on network and cable news. I don't know them, and I don't know if they know this, but what I'm saying to you is that what I'm saying to you is known. So it's not a secret. It's just not popular to have these conversations. If we were honest with ourselves and we wanted to fix all of these, I don't think it's so much about population. And that is part of the narrative that's being driven, is that there are too many people on the planet and we need to depopulate. That is a very popular narrative in some circles right now, and it's frightening. It's frightening. I personally believe that we have the ability to raise the standard of living for every human on the earth today in a way that is sustainable and clean and honest and fair, rather than raising the standard of a few at the expense of the many who are suffering. That's what's happening right now. The way that you do that is you begin to recognize the holistic nature of the planet we live on. We've got to honor these boundaries and others. And when you do that, that thinking is reflected in the technology that you use to create your energy. It is reflected in the way that you grow your food. It is reflected in the way you build your society. Localized living addresses much of what we're talking about right here, rather than centralized living. There is a push for even greater globalization, and the globalization is counter to what the way, the lifestyle that will address these problems. So we're being encouraged to globalize even more, when in fact localized living it's the healthiest way. So when I'm talking about localized energy, draw upon the energy sources that are available to you and your community. One size does not fit all. Solar works some places, it doesn't work in others. Don't force it. There are other things that do work. I'm talking about localized agriculture, so that you have essentially farm to table, and you can do this year round. And the vertical gardens that are now being, they've been around for a long time, but the technology of vertical gardens has grown and advanced so quickly. It's now possible to have vertical gardens growing in indoor spaces that are not vulnerable to the climate the way we've been in the past, without using pesticides and without using fertilizers that can feed entire communities and don't destroy the land to do that and don't have the chemical runoffs. Energy, we have talked about this extensively. I did a series, Missing Links, with the Gaia television program. Excerpts of that are on this YouTube channel. Just a few weeks ago, we had a very controversial YouTube video that I made talking about alternatives to the base load energy that we have today. Base load energy is the vital, sustainable, for sure energy that is necessary for civilization. You can supplement base load energy with renewables. You can supplement with windmills. You can supplement with solar. And I shared with you why the solar and the windmill industry are not clean industries. They are energy intensive, fossil fuel intensive to build those things. They're based upon rare earth elements that are concentrated in a few pockets, primarily in nations that are not the friendliest to other nations that have a monopoly on those. They're toxic to mine. They are toxic at the end of their life cycle. When you throw those solar panels into a landfill and they break up and break down, those toxic chemicals leach down into the landfill, into the groundwater. All of that is in the videos that you'll see on this channel. We have other sources of base load energy. I mentioned the mineral thorium. Thorium is not the answer to all answers. Thorium is a stepping stone. It is a path that is available right now because it is already a proven technology that was used to create energy from the 1960s, 1980s, and were called molten salt reactors, MSR molten salt reactors. So if you Google this, or if you go to Wiki, which is not the best source of information because Wiki is biased through the same bias that's driving much of the media today. You will see through Wiki and other places, Wikipedia, that these are controversial, that they're not proven, that they're experimental. Now, there are new molten salt reactors that are evolving into a new generation of reactors that are experimental, but the principle itself is not. And we had functioning molten salt reactors, again, through the 60s and the 80s. We had them. China, the US, India had them. I think India's may still be running, I'm not sure. So the point is that using thorium as a baseload energy source, zero greenhouse gases it produces. So right there, you've eliminated greenhouse gases. If you believe that's a problem, you've eliminated that. These reactors they can't melt down like Fukushima because they work on a completely different principle. And actually, when they begin to warm, they will stop working because the way the molten salt containers are designed. So they can't melt down. The molten salt reactors cannot produce byproducts that can be weaponized, so you're not contributing to war. The thorium is an element that is abundant in the Earth's crust. It's on every continent, almost in every nation. Maybe not in every single nation, but it is definitely in every continent. It's inexpensive, and it is abundant, and the waste can be recycled into the new fuel cycle. So it's not perfect. Ultimately, we will be using vacuum energy from what we think in the past, what we thought was empty space. That technology is available in some technological programs. It's not commercially available on the levels that we're looking at now. I think we'll probably see it within our lifetime. The point is, if we're looking at Earth's safe zone, if we want to maintain this and if we're serious about it, we already have everything we need to honor these parameters. We don't need to depopulate the planet. We don't need to deplete the small reserves of rare earth minerals that we have already for a sustainable base load energy that works in any temperature, hot or cold. It works if there's sun, if there's no sun, wind, no wind. It can be 50, 60 degrees below zero. It can be 150 above zero, and these reactors are going to pump out continuous power. Economically, we need to decentralize the economies that we have today. This is where the problems are. All of the money that is used in the developed world is linked to governments. And that is the problem. Because when your money, which is a reflection of an exchange of your life energy that you exerted in a task, you rewarded with money, and that money is linked to a government. And as long as that money is linked to a government, it can be manipulated. Interest rates can be raised or lowered. It can be valued. It can be devalued. And all of that is happening to the major currencies of the world today. And that causes suffering to the people that can least afford those kinds of changes because they have no buffer. Many of them don't even have bank accounts. They are living paycheck to paycheck. Those are brothers and sisters that are suffering. We have the technology now, and I've talked about this briefly, through blockchain technology to decentralize our finance, to own our own money, to interact directly, not have it linked to a government. And I want to tell you why I'm so passionate about this, because the money I have in my bank and the money you have in your banks, that money, it's called fractionalized banking. The money that we put in, a fraction of it remains in the bank. The rest of it is lent out at interest, whatever the interest rates are. That money is being used to finance war. It's being used to finance research projects that I know that you would never believe in if you knew about them. You would never support them. And the ones that I know about, I don't like knowing that my money is supporting these things. So, and I'm not saying blockchain is the only way to go. And I mean, Bitcoin. Some of you I know may read that into what I'm saying. It's a possibility, but it will. I don't think it's a currency. We need something that holds value, and I did a video on this recently, that is not linked to a government, that is peer-to-peer, you to me, that's between us, and that we have the ability that is transparent and that is secure, and blockchain technology allows for all of that right now. So, all of this to say, if we wanted to honor these 10 parameters, here's what's happening. Right now, the attempt is being made to try to fix one or another living the same way that we've always lived, just trying to fix what's happening there. If we go to an electric nation, all electric cars, it sounds so beautiful, so clean, and then you ask yourself, where does that electricity come from? Because right now, we do not have the capacity to create that electricity. We don't have the grid to carry that electricity. We don't have the way to store that electricity. And the electricity, much of it is coming from fossil fuels because the other technologies have not advanced to the point where we can replace those fossil fuels. So if we're going to build an electric infrastructure and we think the electricity is going to come from fossil fuels, then we've defeated the purpose. Or, and this is where the politics comes in, and you know, we're a community, we can talk about this. Policies and politics are in place right now to lead people to believe that their industries can be cleaner and greener through carbon offset credits, for example. So maybe you can't meet the greenhouse standards, the non-CO2 standards. So you say, okay, I'm not going to be able to reduce my CO2 footprint, but I'm going to pay a price to do that. Well, okay, so you pay a price, the CO2 is still there. What has happened in the past is that the United States and other Western nations, modern nations, have offloaded our labor, the people that make these products, and the factories to other parts of the world that do not adhere and are not bound to the agreements to reduce greenhouse gases. So if we're really concerned about it, sure, we can offload all of our manufacturing to another country where the labor is inexpensive and they're burning coal to create the windmills, for example, or they're burning coal to create the copper, all of the copper that is needed in these electric cars. You can do that, but you got to be honest with yourself. Are you really honestly addressing the problem, or are you just shifting it from one place to another? So I'm just being honest about. Let me ask this: how can we solve the problems if we're not honest about the problems? How can we solve the problems if we're not honest about the problems? And I want to be honest with you because you, my community, are asking me the questions and you want me to be honest. I'm not a political person, but I recognize that greed is driving us into a way of thinking and a way of living because they've hijacked technology and media to inundate and indoctrinate young people into a way of thinking that supports these ideas. And it's effective because the TV commercials, man, I got to tell you, even I'm drawn. They're sexy. They are the special effects. They are mesmerizing. I mean, who wouldn't want some of these technologies? And then you ask yourself, where's the electricity come from? Where do the rare earth minerals come from? What about the 8 and 12-year-olds with no protective clothing, barefoot, standing knee-deep in the water in the mines in Africa, with their hands digging in the mud to find a few chunks of these rare earth minerals, to give them to the elders that are going to sell them to another country to refine them, to put them into the chips that we're using so we can feel good about having green technology. That is the reality of what we're looking at, and it doesn't have to be that way. We have everything we need to create abundant energy, zero greenhouse gases, inexpensively and equitably so that everyone has it and no nation can hoard it. We have everything that we need to create a financial system based upon an economic system, two different things, that is no longer centralized and controlled and regulated and manipulated to hurt people the way that money is being weaponized today, and you all see that happening in your world today. And we have the ways to grow the food in a way that keeps it local and fresh, doesn't have a huge carbon footprint. Maybe I don't get blueberries in the middle of December that come to me from South America, because that's what happens right now. I get blueberries year round in my local market. And then I look and say, man, where did these come from? Because they're out of season. Well, they came from below the equator where they're in season. And, you know, of course, we all can appreciate those blueberries, and I love supporting my brothers and sisters in agriculture in South America. But there are other ways to do it without the huge carbon footprint of the jet that has to bring those blueberries all the way to my market and the trucks that bring it, you know, from the airports or wherever it comes from. So you see where I'm going with this. We have everything we need to make the changes we need to honor these 10 parameters. It requires a shift in thinking. And to have that shift in thinking, we've got to be honest with ourselves and one another. All of these topics are coming up in the United States in a midterm election. The data will be hijacked and it will be politicized, and a narrative will be created. And when that happens, I want you to think about this conversation and not be angry. This isn't about angry. Just to be honest with yourself and informed, and to do your best to inform maybe your family or your community, and to make choices in your life that help us to live in a way that makes sense, to live locally, to live responsibly. And it doesn't mean you have to live primitively. I'm not saying that at all. I don't want to live primitively. I don't think we have to. We've reached a point in our civilization where we have everything we need to raise the standard of living for every man, woman, and child in a clean, sustainable way without depleting the vital resources